Hi, I'm Richard Sanger, and I'm presenting our work towards transforming OpenFlow rulesets to fit fixed function pipelines. This is work I carried out as part of my PhD research with my supervisors Matthew Luckie and Richard Nelson. So the problem that this work is looking at is that today in SDN, some hardware devices only support a limited set of OpenFlow features, in particular fixed function pipelines. And to add support for these in an application, a developer needs to modify the code manually. So the question we're asking is, can we improve this situation by using a technique to algorithmically transform an existing rule set to fit a new fixed function pipeline? So fixed function pipelines, of which you're seeing the Broadcom OFDPA2 pipeline, or at least a portion of it, are designed to be as cheap and fast and power efficient as possible by using application-specific integrated circuits. In doing this, they can provide strict bandwidth and latency guarantees that other hardware design can't quite meet. They also tend to provide the highest bandwidth and port densities. But the trade-off here is that the tables in them are specialized to perform specific forwarding tasks. For example, the bridging table shown here can support in excess of 100,000 entries, but those can only match Ethernet destination and VLAN and perform an output action. This makes the table large and fast. However, a more generic table like the ACL table supports matching all header fields, and most actions can only store 2000 entries because it needs to use TCAM, a more expensive type of memory, and the match is a lot wider. So the key limitations that make fixed function pipelines hard to fit rule sets to is that they have these specialized tables, which are restricted in the matches and actions available. The order of these tables is prescribed by the hardware design. There is limited or possibly no metadata support. I'll get back to that later. Actions may also be overwritten in these pipelines. So in OpenFlow, this is write actions and the packets action set. What this means is you can add a forwarding decision and then have a table later in the pipeline reverse that decision or override it. And in particular with the OFDPA Broadcom pipeline, they have no way to directly output a packet. Instead, they all have to go through groups, OpenFlow groups that is. So to show kind of the difficulties of this problem, here's an example. So as input to this problem, we have a rule set. For our implementation, we're using an OpenFlow 1.3 rule set, and we have a description of the target pipeline. To do this, we're using table type patterns. The algorithm we are making goes in the middle here, the rule fitting solver, and its job is to try and find a new rule set that meets both the requirements of the forwarding from the input rule set and the requirements of the target pipeline. It is not enough to simply fit each rule individually into the target pipeline, and this is what I will demonstrate. So this target pipeline here has two places where we can put the pop VLAN action. It can either be placed in the first table or the second. And if it's placed in the first table, the VLAN cannot be matched in the second table as it has been popped. Whereas if it's placed in the second table, you can still match the original VLAN in the second table, as it is not popped until the end of processing by that table. So this means that for each individual rule, there are two places two different ways we could try and fit these. We could either put the pop VLAN in the first table on ingress, or we can put them in the second table on egress. And now if we consider that with both rules shown in that input rule set, what we find is that only one of these combinations works correctly and results in that same original forwarding. If we pop the VLAN on ingress, what we end up with is two rules in the second table with the exact same match, as we can no longer match the VLAN. But these rules have conflicting actions. They output to different ports. Whereas if we install both as with the pop VLAN in the second table, this is not an issue because the match in the second table includes the VLAN and can differentiate these two cases. This is where metadata has been helpful to other solutions in the past. So flow adapter and flow converter are existing algorithmic approaches to this problem, and they heavily rely on metadata. And this allows them to introduce metadata, set a custom value to differentiate these two rules in the second table. But because pipelines like Broadcom pipeline and fixed function pipelines in general don't tend to have full OpenFlow metadata support, we are trying to solve this problem without using metadata. So we've divided this problem up into two stages. The first stage is to find transformations of the individual input rules. And then the second stage is to then find a combination of those transformations that has the correct overall forwarding. But first we'll start with the pre-processing that we do to the rule set. The pre-processing is to try and simplify and reduce the size of the problem. And we have three steps. We convert the multi-table input rule set down to a single table. We remove all unreachable rules, and then we compress the rule set. So conversion to a single table, we do that by taking the Cartesian product of the rules across the tables. And this is very helpful because it means that forwarding decisions that were originally represented by multiple rules spread across multiple tables are now represented in a single rule. These rules do remain priority ordered and will have overlapping matches, and there can be a worst case expansion of the product of all rules in all tables in this process. We then work through this rule set and remove unreachable rules. This includes cases where one rule fully shadows, so is a superset of another rule, and also cases where multiple rules combined will stop packets reaching another. Prefix matching is a good example of this. We then created a novel technique we've named rule set compression to try and group similar rules together and solve the problem for just one of those similar rules. So these similar rules will come from like a host being learnt, and we expect these rules to be installed with the same priority, the same match mask, though maybe a different value of that match, and these same actions. With these groups, we create groups out of these similar rules. We then refine these groups to ensure that the dependencies, so that is which rules shadow another or match overlapping sets of packets between groups, are all the same for all rules in them. And then from these groups we select one rule to represent the all those similar rules in each group. So now we've got this single table pre-processed rule set. We then move on to finding transformation of one rule in this input rule set that fits the target pipeline. So we use the term placement to refer to a rule in the target pipeline in one table, a single rule, and then we create transformations of the input rules by joining multiple placements in the target pipeline together. And the idea is that each transformation will have the same forwarding behavior as the original input rule. And then the next stage will pick a combination of these transformations that has the correct overall forwarding. So to find the placements of a rule, so this is the input rule into a single table in the target pipeline, we basically go through all combinations that that table allows. The result of this is that some portions of the rule will be placed and other portions of that input rule will remain unplaced. So in this example, Ethernet destination is not supported by the target pipeline table, the table in the target pipeline. So that is always unplaced. This is the same with the output action. However, for fields that can be matched, for example, the input port, we will create a variation of the rule both with the input port match and without. From these placements, we then define two different types of transformations. A direct transformation needs to be a fully placed rule. That is to say, there are no fields or actions or matches remaining unplaced. And that can be placed in any table in the pipeline. It doesn't necessarily have to be the first. And the idea is this is useful to install policy rules where we don't mind how packets get to the table, but we want to apply a forwarding decision or firewalling decision to all packets that go through a table. The other way we install create the transformation is a split transformation. This must start in the first table, and we form a path by following these placements, following the goto instruction on them through the tables. And we basically just try all combinations of placements to find these and filter it down to the set that have the correct forwarding, the same forwarding as the input rule. So now at this point, we have a list of transformations that we can choose from for each individual input rule, and we are then looking to find a combination of transformations with the correct overall forwarding that matches the input rule set as a whole. Simply trying to do this by checking the forwarding behavior of all possible combinations quickly becomes intractable. It scales with the number of transformations we've found on average per for each rule to the power of the number of rules. So this grows quite quickly. So what we decided to use and settled on was a Boolean satisfiability solver. So what we do is we express this problem as a Boolean expression, and we add constraints to that expression to try and narrow down to include only the most likely solutions where the correct forwarding would be observed. The initial constraints that we add to the SAT problem to narrow down our search is that we must pick one transformation per input rule. This can either be a split or a direct transformation. And then we filter out known conflicts. So we filter out same priority placements with conflicting actions, as that's undefined behavior in OpenFlow. We do not allow fully shadowed placements with conflicting actions because that would be redundant. We also ensure that all tables require an explicit table miss rule, and we select all built-in rules. So fixed function pipelines might have built-in default behavior that you cannot override, and these must always be selected. And then we have variables in that SAT expression which represent the placements of rules that have been chosen, and a way of defining a unique solution, because there will be cases where rules are unreachable and do not contribute to the actual forwarding behavior of the solution. So we can filter down and stop exploring the same result multiple times in slightly different ways. So now we have these constraints. What we do is we run the SAT solver. This returns a candidate solution, a list of placements. We then check the equivalence of the forwarding versus the input rule set. If they're the same, we're done and we've found the valid solution. Otherwise, we inspect where different forwarding occurs, and we correlate the forwarding path that should have been taken through the input rule set with the path that was actually taken through the candidate rule set. And we then incrementally add these as constraints to the SAT problem to disallow this known conflict in future solutions. Our implementation is completely open source and available on our GitHub, github.com/wandSDN. The OF solver project is the main solver. It's approximately 4,000 lines of code. We also created a table type pattern library, which is what we use to represent pipeline descriptions. We use minisat2 as our SAT solver and satisfy to form our Boolean expressions for that. And the equivalence checking is work we published last year to SOSR, and we use that library. We have also released our evaluation artifacts. So for evaluation, we found during development that this technique generally works and finds solutions with some caveats. So our evaluation focuses on how the techniques we developed reduce the solve time and if they're working effectively. So basically we're asking, do the SAT constraints actually help? Are they making it faster to solve? And are they only removing invalid candidate solutions and leaving the valid solutions? We also evaluate rule set compression. Our evaluation is a pretty basic setup. We run each experiment 10 times with a warm-up run to load files into memory. And we limit the test to exploring the first 10,000 candidate solutions. And we perform these tests on 2 different pipelines, both of which are synthetic, though one is based on the OFDPA pipeline. This is the 5-table pipeline based on the OFDPA pipeline, and it maintains the complexities present in the OFDPA pipeline. It starts with a termination MAC table, which determines whether a packet is to be routed or switched. It then splits into 2, routing and switching, goes through our TCP filtering table, which is the ACL table, and then finally packets go through the learning table. This example shows the rule set with 3 hosts learnt. We made a contrasting pipeline, the 2-table pipeline, which basically tries to do everything in the opposite order or as differently as possible. We put the TCP filter in first rather than partway through the pipeline, and then we combine all the forwarding into a single table, whether it's routing or switching. And here are the results from our experiments looking at the SAT constraint performance. So in this table, the less constrained run is the first row, and reading down this table, we add more and more of those constraints that we listed earlier to check that they're actually being effective. So if you look at the solver time, overall, the solver time decreases. So this is milliseconds, so we've gone from 13 seconds down to 128 milliseconds. And at the same time, if you look at the number of unique solutions found, aside from starting at 7, it maintains a constant 10, meaning that we're not removing valid solutions with our constraints. And the reason it is 7 to begin with is that we limited this test to explore only the first 10,000 candidate solutions, if we had have run it for longer, it would have found all 10. If we look at rule set compression now, we also found this to be very useful. So that rule set, the 5-table rule set that I showed earlier, if we look at that with 50 hosts learnt instead of the 3 which were shown on the slide earlier, the compressed versus uncompressed performance is 12 minutes to run versus 6.1 seconds when compressed. So there's some very large gains there. Although that of course is a synthetic rule set, we also looked at how well compression works on real-world rule sets. For this we used 2 faucet rule sets, one being an access switch and one being a router. And we saw 97% and 83% reduction in size of those rule sets. So even with real-world rule sets, it's making a pretty significant difference. That is reduction in size of the rule set, not reduction in solve time, which could be larger. So future work and kind of the real world issues we run into with this research is that the rule sets and pipelines for real world cases are very large. So there's no good way of knowing if a solution doesn't exist or if we are simply not finding it because we haven't considered a certain case or we are incorrectly adding constraints to our set solver that is removing a valid solution. And simply checking all possibilities or all combinations of transformations is intractable, as we've kind of mentioned earlier. We also find that real-world pipelines, like the OFDPA pipeline, tend to use non-standard OpenFlow extensions. This is something that our solver currently doesn't support. It only supports standard OpenFlow. So it's not kind of capable of dealing with that. This technique is also not suitable for flexible pipelines because we enumerate all possible combinations and search them all. Whereas of course with a flexible pipeline there are going to be many more possible combinations and this would very, very quickly become intractable. We also need further research to look at the support for incrementally updating the rule set and how stable the output is. In comparison to related work, as I mentioned earlier, flow adapter and flow converter are the most similar to ours, and they avoid that whole second stage of trying to find a valid combination of the transformations, or at least make it a lot easier for themselves by using metadata to link rules between tables together. And then the other kind of common approaches to this that we've seen is either just updating your code manually or trying to code to a kind of virtual pipeline in the middle. So Nozzix and table type patterns kind of present this idea of using a pipeline in the middle, which both the controller and switch would need to support. The problem with this, of course, is that this requires manually updating code for both the OpenFlow switch agent and the controller or control application. So in summary, we've presented a new rule fitting approach which doesn't rely on metadata. We've demonstrated a number of new techniques to reduce the size of the problem. This includes using a SAT solver to constrain the problem and rule set compression. And we've released all of our source code and evaluation artifacts. If you have any questions, you can direct them to my email. I believe there will be a Slack channel up, and that's the link for the source code. Thank you.